Our first session is going to focus on GeoAI, Future of Connected Systems. And to lead this discussion is Chris Tucker. Chris, welcome to you and your panel.
Thank you so much. Awesome. We're all mic'd up, so we may just wander around. There's no real rules when you have a lavalier mic. I don't know why I just walked this direction. But I guess we get started. Do we have to push our buttons, or how does this go? Hey, look at this. So I'm Chris Tucker. When I'm not being the chairman of the American Geographical Society, I'm the CEO of a company named GeoRobotics. And I'm going to chat a bit today about GeoAI and the future. Oh, thank you. Turns out I have a man crush on Pete. We'll talk about that later. I'm going to talk about the future of connected systems. And you may say, what the hell is that, Chris? That's what I'm going to talk about. So it turns out, when I got started in this industry 25 or so years ago, we had lots of grainy old images that described what we thought we were doing. So I pulled one out of the archive here. And I worked with this strange organization called the OpenGIS Consortium. And they were awesome. You talk to them about how can I make this thing work with that thing, right? Interoperability. And they were working on standards. And it turns out we're weirdly fortunate to have both the chairman of the now Open Geospatial Consortium, Ed, raise your hand, and the COO, Christy, raise your hand. Two leaders in our field. Thank you so much for showing up. But a quarter of a century ago, the Open GIS Consortium was really a leader in what we then called sensor webs. And as you can see from this grainy photo, right, you could have all sorts of different kinds of systems out there that observe the world in different ways. And they existed in space and time. And how do I share all of that, those sensor observations from those various systems? At the time, we never called them systems. They're all sensors. They're all sensors. How do I bring that all together over the web? And that was the age of sensor webs, I like to call it. And this is super nerdy, and I don't even know if our geography teachers maybe like, get this guy off the stage. This is just weird. But if you think about all those sensors, the sensors you have in your house, the sensors you have in your pocket, the sensors you have in your car, right? They actually do three things all the time. They sense the world, right? Something wiggles in the world, and I can turn it into zeros and ones. It processes. How do I take those zeros and ones and turn them into some other digital thing? How do I take that picture that it took and turn it into an alert, right? But also we have actuators. How can I take a command of something somebody does out in the digital world and make it an action in the real world? And I think people don't, it took me almost like 15 years to kind of, the great Mike Botts would take me out to lunch, and he's such a nice guy. He would explain this to me, and I never understood it. But really, every one of these systems, whether it's your phone in your pocket, it's your car, it's that home security system that you have, we have all of these systems out there now that are observing the world, processing on it, and letting you take action in the world via the system in space and time. All right. So we really moved from this old school. I love all the grainy, the grainier like the old images can be, the better. Like, it lets me understand how old I am. But the OGC's sensor web enablement architecture has, in just this last year, become the OGC connected systems, OGC API connected systems. Somebody said I shouldn't say the word API yesterday, but they did, and now I'm doing it. Application programming interface. It allows machines to talk to machines, right? Through a standard way of talking. So we've really moved from the age of sensor webs to the age of connected systems. And what's fascinating is when we started a quarter of a century ago, those systems, they did process. You know, they had some sort of processing on it, but there was no GeoAI. There was, well, I mean, I'm sure there was AI out there, but we certainly weren't touching our systems and everything. And now we've entered this really strange world, novel world, interesting world, where the smallest system deployed on your phone, on a Raspberry Pi, like a tiny thing out there in the world, can not only observe the world and process on those observations, but then take action. It's really pretty incredible what's going on. And you can put GeoAI processes on the smallest computer known to man. Whether you're processing on video, or whether you are taking action on something that's coming in. And so we're going to have a little discussion today about all of those systems that are out there, like these. I just pulled this out of our georobotics slide deck because people go, what do you mean systems, Chris? And I go, oh, I mean systems. I mean all the systems, right? Space, air, land, sea, cyber, electromagnetic. There are sensors and systems out there that sense the world in every possible way, that operate in our skies, that operate in our oceans, that operate all across our land. They sense things not only in cyberspace, but also electromagnetically. If you're not an electromagnetic nerd, I mean, you will be, right? Everything you emit is electromagnetic and can be sensed by sensors. So, we like to talk about data streams of observations that come off of these sensors and control streams of commands that can go to them, right? I can drive a robot, I can fly a drone, I can task a satellite, I can unlock a door, I can slew a camera, I can invoke a process, I can deploy an effect. These are things that we can all do. We all can now do these things in an increasingly connected world. And what's weird about it is what used to be a basic process, I could put a little math process on a sensor maybe 25 years ago. I can now deploy an entire GeoAI computing stack on a Raspberry Pi on an ocean sensor. And I know Tosca does that all the time, right? Just for fun in her spare time. So GeoAI is this fascinating thing. It's this thing that's changing our world at the edge. Maybe that's a DoD term, but like at the edge, far, far away from anything, right? Far, deep in the oceans, out in our transportation infrastructure, wherever the hell Esri feels like doing something, right? At the edge, we have GeoAI sitting there on these computers doing things. It's supporting autonomous navigation, and that's not just a car anymore. It's increasingly things in the sky. It's things in the ocean. It's things across our sidewalks, right? We have autonomous systems. It's collaborative autonomy because those systems don't just do what they want to do. They do what we ask them to do, and we partner with them, and then they partner with each other. That's a kind of an increasingly interesting world. And how do I then have GeoAI do system orchestration, where I have a drone following a human to keep them safe in a particular environment, right? So this is just a bunch of words. Thank you, OGC, for having websites that do these things on the public web that make it easy. But I just want to point out, right, so GeoAI isn't just something you do with all the data being collected about the world. I feel like that's a lot of the presentations we do is say, wow, I collected all this data, and I did some GeoAI on it in the cloud, and it was amazing, right? It turns out that GeoAI will be at the center of a future defined by increasingly connected and increasingly autonomous systems with which all of us humans will collaborate as we reshape the geography of the planet over the coming decades. So that's my little intro to our little discussion. I'm going to pass it over to Tosca, who does awesome things in the ocean. Tosca.
Thank you. Do I get the little clicker?
I think you do. I think you're the
Excellent.
clicker person now.
Okay. Let's see. Oh.
Whoop, whoop.
Oh.
Whoop, whoop. It's coming soon.
Okay. Coming soon. Stuff about the ocean.
Stuff about the ocean.
Awesome. Okay. Is this showing up?
That's you.
Very cool. All right. Hi, everyone. I'm Tosca. I'm with a company called Sofar Ocean. And we do what we call ocean intelligence. And that is learning as much as we can about the ocean, what's happening today, but also so that we can predict what's going to be happening tomorrow and in the future. Because whenever there is uncertainty, there is opportunity. If you have a better idea about what is going to happen, you can be smarter, you can be more efficient, and you can have a strategic advantage if you're in some type of competitive aspect. So why do we go and collect data about the ocean? Well, it turns out that the ocean is relatively undersampled compared to all the other data that we collect, both in terms of geography, but then also just in terms of in the world, the data that is collected. If you think about all the data ever collected throughout humankind being the distance from here to the moon, the data collected about the ocean would really only be the length of a football field. So it's just this tiny fraction. And the reason for that is because it's really hard to collect data in the ocean. It's a dynamic environment, it's a harsh environment, it's vast. It covers 70% of the ocean, or the Earth's surface. But we really should be planet ocean, right, rather than planet Earth, because it's covering so much of this planet that we inhabit. And so traditionally, collecting this data, because it's such a harsh environment, required these really big, sophisticated, complex, expensive, difficult to maneuver systems, kind of like the buoy that you see up on the screen right now. And that led to, because they're expensive, very sparse observations. And we do what we can with those observations. There's amazing organizations like the National Data Buoy Center that run observation networks. But because the data is so sparse, there's limitations to what we can model and predict in the ocean. And so really the reason Sofar was founded was to answer this question: what if connecting the oceans was easy? What if it wasn't expensive? What if it wasn't hard? What if you didn't have to have special training to be able to go out and collect data? What if we could turn the oceans into something that citizen scientists could be helping us collect data on? And so the founders of the company developed this connected system, the spotter buoy, which you can see in the photo here. I thought about bringing one myself, but ultimately decided, taking on Amtrak would be a little bit of a pain. But it's just the size of a basketball, so you can kind of see that in the photo, powered by the sun, and it sends data back in real time. And what we can do with that data is power GeoAI. So we have deployed thousands of these buoys globally. We use those to inform ocean prediction models, and that could be marine weather models, but it can also be ambient sound, and I'll get to that in a moment. There's a really cool company called AOS you'll be hearing from later today, and they're doing ambient sound modeling. And then those models can be used to drive decisions. So at Sofar, we have a platform called Wayfinder. It's like Google Maps, but for the ocean, but Google Maps on steroids. It's like for your specific vessel, given the exact weather conditions, what is the optimal route that you can save fuel, which saves money and also reduces carbon emissions. So really, when we have this ability to predict what's happening, we can have a lot of advantages, both for the climate, for the economy, and many other benefits. So the spotter buoy, we started off just sensing on the surface, but have been able to add the ability to plug in additional sensors subsurface. One example of that is a smart hydrophone. So you were just talking about processing at the edge and what's possible now. We can actually run AI, ML at the edge. And so AOS has developed a hydrophone that plugs into our buoy that you can actually run AI, ML models at the edge to alert, but also to better understand when we have these connected systems, think about it beyond just a single buoy, what that single buoy is sensing, and think about the network of buoys as the sensor and the predictor. And so what you can see on the screen here too is also we can have the ability to model how sound is propagating. And so we can better predict, okay, if there is an event happening, given what we know about the way that sound propagates, what does that mean about what vessels might be involved or what kind of event is happening? So we really need this ground truth to have those better predictions, and that's why we deployed all of these buoys around the world. We have an ocean science team that assimilates this data and runs marine weather models that end up being 50% or more accurate than other leading weather models, and that's purely because we have access to data in locations where previously there was no data, and that data is our ground truth. If we don't know what's happening today, we can't predict what's happening tomorrow. And like I mentioned, we use those in our Wayfinder platform. And just to give you an idea of what the impacts of this are, I'm not going to read all of these statistics, but we can really have a massive impact shaping the future geography of our planet when we have a better idea of what's going to be happening in the future. So with Wayfinder, if you think about a ship going from one side of the ocean to the other, they can save so much fuel and get to places faster if they avoid adverse waves and take advantage of favorable currents. And it's such a simple thing. If I actually go back a slide, you can see it's just a really minor tweak oftentimes to their route, but that has an immense impact in terms of reducing carbon emissions. And these types of applications extend beyond the commercial shipping industry. We can optimize so many things. So if you think about optimizing wave energy or wind energy, you can tweak the way that you're positioning your wave energy converter if you have a better idea of which direction the currents and the waves are coming from. And so you can get more energy out of it. So we have more clean energy, and we can be driving this cleaner planet. So another thing that you can unlock is new ways of thinking about routing. So in this photo, it's a little bit hard to see in the background, but this was taken on the bridge of a ship called the Berga Olympus. And the Berga Olympus is actually a wind-powered commercial shipping vessel. So those vertical sails, they're kind of funny-looking sails, but without really accurate weather prediction capability, this ship would not exist because it's difficult to capture the wind to power such a heavy and immense ship. And so they were so excited to have Wayfinder at the ready for them to be able to take advantage of the favorable winds and reduce the amount of their carbon impact. You can also have an impact at the local level. There's this amazing organization called Backyard Buoys. It's in partnership with NOAA, and they provide connected systems, in this case our spotter buoys, to indigenous coastal communities that traditionally didn't have access to data about the oceans right outside their doors, even though they depended on those oceans for their livelihood, whether it's whaling or fishing, depending on the community. And these are also communities that are at the forefront of climate change. They are at the forefront of sea level rise. And now they have access to data in real time, but also better predictions about what is going to be happening as the climate is changing so that they can make better decisions for their community in the long term, but also in the short term. Like, hey, should we spend the fuel to go out fishing today? Or maybe it's, the weather isn't looking too good. Let's stay home and save that fuel. You can also, monitor coral reefs. There's an amazing organization called Aqualink that has positioned spotter buoys at coral reefs around the world to monitor them for heat stress events. And again, this predictive capability, if we have a better idea of what is going to be happening, then we can take preventative measures. You can also improve hurricane prediction. So we actually developed an air deployable version of our buoy so that it could be deployed into hurricanes and improve our ability to know what's going to be happening in terms of storm surge. So this was actually ahead of Hurricane Ian a few years ago. And we can also access data in the most sparse and harsh parts of the Earth. And so we partnered with the Coast Guard and the Navy to get our buoys into the Arctic and down into the Southern Ocean around Antarctica. These are areas that are essential for understanding climate tipping points. And so having this data is enabling us to better understand what the ripple effects are going to be as those changes ripple out throughout the globe. And at a nationwide level, Australia has really leaned into connecting their coastlines. And so they've deployed more than 40 of our spotter buoys around their coasts for everything from climate resilience to for the surfing tourism industry, we want to have a better idea of what the surf is going to be. So there's really so many things you can do once you have access to the data right now and the data in the future. So this is called Geo 2050. It's a GeoAI conference. And so what I wanted to end on was, where are we going to be 25 years from now? And so to think about that, I thought about, well, where were we 25 years ago? 25 years ago, if you had said that, hey, there's going to be this tool that you can have in your pocket that if you ask it literally any question about any book ever written, you can get an instant answer, people would think that that just sounds insane, right? In the year 2000, right? Like being able to just pull a tool, like a smartphone out of your pocket and ask it any question about any book ever written and get an answer, like that seemed magical, but it's possible today. But what's not possible today is to get every question about the ocean answered. There's still so much we don't know about what's happening under the seas. There's still so much we don't know about how the ocean dynamics are playing out as we go through climate change. But what I believe is going to happen as we approach 2050 is that we will have these connected systems that can give us these predictions, that can give us a better understanding of what is happening. And so you will be able to ask any question of the ocean and get an answer. So thank you.
All right, Khrystyna. And so far it's awesome because, I mean, come on, right? And now we've got Trimble. So who here knows what Trimble is as a company? Raise your hand. Awesome. All right. So those of you who don't, I have a crush. Well, I have a crush on Ian Warner. Where's Ian? Is Ian here? I have lots of man crushes. Anyways, AGS counselor Ian Warner, and we have Khrystyna here from Trimble to tell us about all the awesome things, the way Trimble thinks about the future of connected systems. Go ahead.
Thank you, Chris. Hello, nice to meet you. Yeah, sorry for being late. Never trust Uber in New York City. Use Subway. This is my takeaway from today. Yeah, so Trimble is very famous for its hardware. We have scanners, we have mobile mappers that can collect point clouds, images. It's very accurate, high resolution data, right? But do we actually provide a solution to our customers, to our society by providing the data, right? I don't know any person who would collect a point cloud or who would collect imagery just to upload it and look at it at their computer screen, right? What you're actually looking for is information that you can extract from this data. And AI helped us to transition from data providers to actually solution providers. So we can solve industry problems, we can solve society problems. And my team has worked with many groups in Trimble. We provided solutions for railway, for tunneling, for energy. You can see here examples of how we work with the utility groups, with the construction. Today, I would like to talk in more detail about transportation infrastructure. Transportation infrastructure is critical for economic growth. It is critical for public safety, for public transit, mobility. And just in the US, there is more than 4 million of highways and roads in this infrastructure. And more than 40% of these roads and bridges are in less than ideal condition. More than 50% of this infrastructure is aging. And Federal Highway Administration budgeted $70 billion for 2025 to construct and maintain transportation infrastructure. We in Trimble decided to transform the way the transportation infrastructure is managed because it's very critical. Public agencies need to make sure that this infrastructure is efficient, and most importantly, this infrastructure is safe for transportation users. Our ecosystem for transportation infrastructure spans from rapid data collection, and then key point is the AI-based analysis or feature extraction. So you can extract information about the condition of your assets, the condition of your roads. You know exactly where you have the problems, and you can respond to these problems rapidly. Once information is extracted, this information goes to design, construction, and maintenance teams so they can operate, and they can make sure that our transportation networks are in good condition. For data collection, we have mobile mappers. Mobile mappers are systems, complex systems that are mounted on the cars, and they collect point clouds at highway speeds. They also collect the imagery, the dedicated pavement imagery and panoramic imagery. This is a great way to collect your data in a safe and efficient way. You just sit in the car, drive, and you can collect thousands of miles very fast. Well, it's great, right? You collect all this data, you end up with terabytes of point clouds, you end up with tens of thousands of images, but then what? You uploaded this to your computer, and now you have to figure out what to do with this data. That's definitely not something that you would like to do, right? So we use AI or GeoAI to transform this data into information about transportation assets. And the first step is automated identification of assets. We developed multiple 3D deep learning models that can automatically classify point clouds into various classes. It can be bridges, overpasses, pavement, curbing, traffic signs, poles, power lines. You can achieve any level of granularity that you need. So you identify every asset in your transportation network. The next step is identification of assets vectorization. So what you actually need is automated vectorization. You need to create lines, you need to create points for your curbs, for your brake lines, jersey barriers, traffic signs, poles, power lines, and you also need to assign attribution to them. How tall is your tree? How tall is your traffic sign? what kind of traffic sign you have. Is it a stop sign? Is it a speed limit sign? What kind of lane line do you have on your road? So this is the step where you get this layer of information. So this is what you get with AI right now. But where we move in is condition evaluation. Because asset inventory is great. It's helpful. You know where your assets are. But what you actually care about as a public agency or as a transportation user who uses this network every day is in what condition this asset is. OK, I know that the stop sign is at a certain intersection. But is it still reflective? Can I still see it at night? Is my striping still reflective? Can I see it at night? Do I have any major potholes, cracking, or ruts that might be a driving hazard? I might have an accident because of that. That's what I actually care about. And that's where we are going with our GeoAI. We want to help not just create an inventory of assets for transportation infrastructure. We want to tell you how good is that or how bad is the condition of your assets so you can take action, so you can actually serve your community. One of our key workflows is automated pavement inspection. The software consumes the point clouds and the imagery and the GNSS positioning from mobile mappers. It takes this complex data set and it transforms this into information about the pavement. So we can automatically identify every type of defect on the pavement. We can assign a class to it. Is it a pothole? Is it a rut? Is it cracking? And then we can evaluate the severity of each distress. How deep is your pothole? How big is your pothole in general? How long is your cracking? How deep are your ruts? So you can understand what problems exactly you have. You can evaluate the severity of these problems so you can make sure whether or not the road is still safe to drive. And you can send this information to field crews, to maintenance crews, who can take action on site. The data is very positionally accurate, so the maintenance crew knows exactly where to go and knows exactly what they have to do. Is it a crack? They will need to seal it. Is it a pothole? They will need to fill it. If it's a rut, they will need to go out there and mill it and overlay again. And of course, after that, after you get all of this information about your pavement, it's still quite a lot because you need to aggregate all of this automatically extracted information about your assets. So once it's aggregated, you need to have a system that enables you to do the budgeting, the planning, and that enables you to predict deterioration of your pavement. Because maybe today, the pothole or the cracking is not very severe, it's still not driving hazard. But what happens tomorrow? What happens in a week? I want to have a smart system that helps me to transform this information that was extracted with the help of AI into dashboards. So I know what I have to do tomorrow or in 1 year or in 5 years. And that's where this AI analysis that was applied to geospatial data to all your point clouds and pixels. This AI analysis, it transforms your points and pixels into valuable data. It integrates into asset lifecycle management systems that help you to predict deterioration and that help you to understand how much money you would need to spend on your transportation network. And yeah, this is all from my side. And let me know if you have any questions. I will be today here all day. Happy to chat about it in more detail.
Awesome. Thank you, Khrystyna. So now we have Pete from Esri. It turns out we have friends in common. We just found out in the back. And Pete's been around. You're old school, man. I like that. Pete's going to give us a talk, but I want all of you to think about your questions. We have 2 microphones. When Pete's done, you get to ask questions because your questions are better than mine. Pete, over to you.
Great, thank you, Chris. Good morning, everyone. Today I want to talk about some geospatial use cases from the field to leverage this great data that's coming from these connected systems. I know many of you know Esri, but I saw some new faces yesterday. So very quickly, we provide a comprehensive geospatial platform called ArcGIS. And one of our core missions is to advance the science of geography to give you all tools to pursue the important work that you do. And of course, aligning with what the trends are and the direction, we also are looking at how do we infuse AI into ArcGIS. And very quickly, the way Esri is thinking about it is we actually have our own set of capabilities we call GeoAI. We've been doing it as long as some of those articles that were talked about yesterday. This means we infuse deep learning, machine learning into our platform to enable GIS professionals to use them. But then with the advent of generative AI, we also, similar to the Copilot or ChatGPT experience, we came up with AI assistants to help the professional do their job better. Code assistants, writing Python, writing SQL queries, et cetera. And then was touched upon yesterday briefly, which is very emerging, we're also looking at agentic AI. How do you embed these great geospatial capabilities into smart automated systems of agents, et cetera? But then ultimately, the main goal for us is we want to provide the framework for you all to build these AI tools yourself, to build your own agents, to build your own assistants. So that's really the direction where we're trying to go. Now on to some more specific examples here. So this was recently presented, I think a week or two ago at the Smart City Conference in Barcelona, and I thought it was a great example of connected systems and GeoAI working together. So there's a much better story than I'm going to tell here. I'll just go over very quickly, but Raleigh, of course, did community surveys of their residents, and one of the top issues was traffic flow and transportation. And then they also had ambitions to become a smart city. So this started a few years back, but they started censoring all their intersections. They did some pilots first. And then recently, with the advent of some of our friends at NVIDIA and Microsoft, these vast compute platforms are out there. They can do agentic interpretation of video systems. And a lot of people can do that, but I think what the real important part is the location dimension, right? So you detect an object from a camera, but then plotting that on a map, but then you'll see here in this example, not only detecting it in real time, but then actioning it, like Chris mentioned. So in this case, it's a hypothetical. There's a stalled vehicle that's detected, and then it prompts you to say, what do you want to do? And it says report an incident, or the incident may clear itself, and you don't have to action it. So this is just a great example of these connected systems working together, but with that geographic dimension as well. This is just a brief overview of the architecture. I'll skip through this, but yeah, there's some really great capabilities coming with NVIDIA and Azure, so the tools are there to do these capabilities. Another great example is GeoAI, and we call oriented imagery. So what some were talking about, this can be street level, panoramic, 360-degree, whatever you call that, and I would call these connected systems as well. This can come from drones, from aerial street-level imagery from the Trimble vehicles we just saw, or even ground-level imagery. And this is a vast treasure trove of information, but it can be hard to pull together, right? So a lot of times it's sitting there on a hard drive, you're not really getting value from it. So the question is, how can you bring all that together and use GeoAI to get value from it? So I'm not going to pretend I'm not a data scientist, so I'll probably botch this, but this is what our team put together to explain the concept of just really leveraging what the industry is doing. And they use this concept of embedding, so taking a picture of something, the machine translates it into a series of numbers, and then that gets into this vector database, as they call it. And really that gives AI the language to communicate and map things to the real world. So we could take that concept with that oriented imagery, the whole collection of imageries, use a lot of the foundational models that are out there, load it into a vector database, and then you can start just using prompts without pre-training that imagery, if you will. So here's an example. The city of Detroit graciously lent us some of their panoramic imagery. And you'll see here, there's typing a keyword trash, right? And then when they run the prompt, it not only is finding that in the imagery, but also plotting it on a map, right? So that's so you can actually see where these occurrences of trash are occurring, if you will. And the benefit of this is that there's a lot of use cases. We just started looking into this. There was actually a great emergency management one, but I couldn't get permission to show it, of drone and ground imagery responding to some of the weather events happening. And this is great for finding, helping find victims, debris, et cetera. And then here's another example of even interior mapping. These days, a lot of people have these backpack devices. They map the interiors, and imagery comes along with that, right? So imagine you could say, look for defibrillators, et cetera, right? So a lot of technical examples, but the real challenge is trying to find those good use cases to apply that to. Another example is using foot traffic analysis. And for better or for worse, there are a lot of companies out there that are, in this case, the connected system is your cell phone, right? That's always emitting location from Wi-Fi or GPS. And a lot of these companies, in this case, the one we have a demonstration of is Placer AI. They then enrich that with demographics, location data such as POIs, and then from there you can drive insights, patterns, and I'm going to use the dirty word, also just APIs that can feed into other systems. So here's a great example of using generative AI combined with foot traffic data to look at, for commercial purposes, who's visiting this Starbucks, right, for site selection of businesses. I've seen some other use cases in parks, for example. They want to know, which events or which areas of the park are attracting the most people, and maybe they need to focus their asset management or maintenance efforts more in those areas. This last example that was touched upon yesterday, which I think is really exciting, is GeoAI and supply chains. And once again, I'm probably going to botch this, but there's technologies now called graphs, and it was really pioneered by the social media companies. That's how they figure out who to say connect with this person, who's related to this person. But then people started applying that to other use cases, right? Like people networks, transactional networks, knowledge networks, and guess what? Supply chains are a perfect graph implementation. And then this graph technology brings new analytical capabilities that can be sometimes harder to do with traditional relational queries, joins, et cetera. It can actually find things more efficiently because it's a more natural language to find relationships. So what's really interesting is that there are also a great potential for geospatial AI. So Esri has come out with a product called Knowledge that takes the graph, but also, again, applies the location dimension to that graph analysis and link analysis. And then the icing on the cake, well, I'll get to that next, but as mentioned, these are great for cyber vulnerabilities, right? If this substation goes, what's that going to impact? Obviously, fraud, waste, abuse, cyber threats. If you think about it, cyber networks are a natural complex graph. And one that I'm really excited about is the asset management and climate resiliency. If you think of all the variables to identify what's at risk, you could have an asset sitting in a certain type of soil in a flood zone that has this many work orders or it's been driven over 10,000 times from a heavy vehicle, et cetera. All is that possible, but it's much easier to figure out the assets that are at risk or most vulnerable using these graph capabilities. But then graphs are also a great data model to wire up to generative AI. So this is just a sample application to just use natural language to interrogate your supply chains. And so you can ask who's supplying what, or if a natural disaster takes out one of our suppliers, what is the impact of that? So I saw some of the speakers yesterday touched on this, and I think there's a really exciting emerging field, and ideally these are all connected systems that you can bring together. So in parting, I would say, this is the future of connected systems. I would say the future is here. The technology is here, but I would argue the harder part is how do we get value from that, right? How do we tackle the right problems? How do you measure success? ROI, how do you do it ethically and responsibly, et cetera. So the people part, I think, was touched on yesterday too. That to me is the hard part, but the technology is there to use. It's just how do we use it in an effective and responsible manner. Thank you.
Fantastic. Thanks, Pete. Awesome. Eddie Pickle, grabbing the microphone.
Good morning, everybody.
Your question's going to be better than mine, Eddie. Go to you.
I'll try. Hey, Khrystyna, that was really great. I mean, they were all great. But I was wondering and maybe I just missed it in your presentation, but what are your data and what is your aspiration? I mean, I could see if you have the data, you can predict things. You can say the remedy for the streetscape or whatever is this. But are you looking to develop services that monitor for a city or a location that's like 24/7, or are you trying to be predictive with AI? Are you trying to be predictive given weather conditions and historical patterns? I can expect potholes to form at these areas. What are your I know what you can do, but what is really practically available now, and what are your aspirations using AI?
Mm-hmm. Yeah, great question. So what is practically available now? You can do monitoring 24/7, of course. Probably it's not very efficient, not necessary for pavements, for striping and signs, but you certainly can do this. You can collect the data. You can understand what is happening now, what is the existing condition of the asset now, and this is the part where we actually apply AI to get this information out from this data, from point clouds and images, and sometimes from GPR as well. But then the asset lifecycle management platforms, this is where this is where the algorithms help you to predict what will happen in the future. This is all already possible today. You can do prediction, you know the existing condition based on your data today. And if you collect data often enough, so if you collect it every half a year, every year, the asset lifecycle management platforms use this data or information already, right? Information that was extracted from point clouds and images to predict what will happen tomorrow.
Great question, Eddie. Who else wants to grab the mic, or do I get to ask an actual question? Awesome, look at me. So it seems to me, at least in my experience for the past 25 years, I remember 25 years ago when you talked about sensors and systems, they were big, they were expensive, maybe a government could afford it or a big corporation, but the rest of us were out of luck. And what's been happening over the past quarter century has been the miniaturization, the commoditization. These have become inexpensive. My team, I know that I just get emails in the middle of the night like, hey, Chris, can we buy this? And it's like $120 on Amazon. You know, like the coolest sensor that does the most amazing thing. And of course, it's kind of weird that the sensor nerds often don't know geo, so there's no GPS, there's no compass, there's no accelerometer, right? So it doesn't collect geospatial data until my nerds get their hands on it, and then they make it do it. But there's this commoditization, and I think Sofar is a great example because you showed the big buoy that they used to have to do, and now you just chuck a basketball-sized thing out there. So we've got 25 years ahead of us between now and 2050. If you think about commoditization, miniaturization, what does that mean for your different businesses?
Yeah, absolutely. I'll just chime in because you mentioned buoys. That was really the goal with Sofar, was this commoditization, miniaturization. There's a few things that drive it. So one is the actual cost of the sensor itself, driving that down. But there's also the deployment costs. So you saw in that photo of the big buoy, you need a huge boat, you need a huge team, it's very expensive to get it out there. So if you drive down the deployment cost, and this can be true outside of the ocean as well, right? Like if you have like a little mini drone that an average consumer can deploy, you don't need special training, you don't need special equipment, that really brings down the cost. And then there's other ways that we're bringing down the cost too. So we designed our platform to be modular, and so the sensors that can plug into our platform can also plug into USVs or UUVs, and that drives down costs too because you're not having to spend a lot of time doing expensive integration. And then the other thing that really drives down the cost is this edge processing and edge AI ML, because sending data back from very remote locations gets very expensive very fast if you're relying on satellite comms. And Starlink is changing the game, but it's still expensive, and you need to limit what you're able to send back to just the important information, the actionable information, and Edge AI ML is enabling us to do that, and that's driving down cost as well.
Awesome. Pete?
Yeah, Esri's not really in the sensor business. We like to leverage the data, but I can give you, to your point of closing that gap, a lot of times the sensor vendors have no concept of the potential use cases, right? So ideally, we want to educate them. I don't have the answer to how to do this, of like when you're installing that sensor, capture the location, or in your feed, you know, like what we've done a lot is building management systems, right? If you have the like room number, unit, et cetera, you can do a natural spatial join to a space. And those are real use cases. Like one example from New York City, they had a building management system sensor. It detected a change in water pressure, and they got to a water leak that if it hit the elevator shaft would have been millions of dollars of damages to that building. But a lot of times you have people that want to do these use cases, and then you're like, oh wait, we got to spend 2 years mapping all the sensors, or we got to fine tune that API to actually get it so you can relate it to a real world location. So I don't have the answer to it, but to your point, that'd be great to close those two worlds closer in the gap, because then you can do some really impactful things.
For sure. Khrystyna?
Well, we always try to look at the sensor and the application, right? And we try to minimize the number of elements in the sensor so that the sensor serves its application, right? Do I really need the camera? Do I really need a dense point cloud? You know, we can have a scanner that produces tons of points, but do I really need it for asset inventory? Probably not, right? What I'm gonna do with that? It's really cool to have it, really cool to see this point cloud, but I don't need it, right? I don't need this expensive scanner that produces billions points. So we try to look at the system, and we would try to make sure that all the cameras and scanners that are mounted on the system are actually necessary for certain applications. Of course, unfortunately, for certain applications like design and constructions, it's impossible to make it low cost because you need a very high accuracy and precision. But yeah, we try our best to look at applications and make sure that with the minimum requirements that we have for this hardware, we achieve the goals that the user would need.
Awesome. I see Ed Parsons, chairman of the Open Geospatial Consortium, standing up. Apparently, your name needs to be Eddie, Ed, or Edwina to ask a question today. Ed, over to you.
Yeah, I won't ask you what Ed is short for, but no. My question is for Pete, and I think you touched on something that's really important with knowledge graphs. I think AI systems are fundamentally powered by the data that they're trained upon. And I think we've not done perhaps a particularly good job in Geo in building semantically rich databases. I think knowledge graphs are maybe part of the solution. So can you tell us a little bit more about how you've been using knowledge graphs? Because I think that's really useful.
Certainly, yeah, like the asset, because that's one, like when we came out with that product, I just always thought that graphs for, like I said, finding the bad guys or gang, things like that. So I kind of tuned it out. I'm like, why do we have a product like this? But then once I started seeing all the potential, if you squint and look at it, so many things in the real world are these interconnected graphs. Like supply chains is a great example. Actually going back to like a law enforcement one, or even like children's services, this was a recent use case a customer brought to us. A lot of times they have to go knock on a door, right, to serve a warrant or something. Like, what are they walking into, right? So a graph can say, I'm going to go, or I'm going to go knock on this one. He's got an affiliated person there. There were 3 domestic disputes at this location, bringing all that together. So I think there's limitless use cases, but I think it's that barrier of understanding because it's a whole new, type of thinking. It's a different query language, and I don't think any of us who are geography people studied graph in college, right? So I think that's the hard part of just educating our industry and of the capability and the power of graphs, and then from there, I think there's huge potential, and they're even just a great natural fit with generative AI, especially in agentic AI. So I think there's a lot of potential, but it might be more, on us to level up our knowledge and creative thinking about using them.
Any other questions? No. Yeah, there's a microphone. You're allowed to do it. This is awesome.
Good morning, Danny Goldstein from Rochester, Talmudical Institute. Just
Awesome.
A quick question. Yesterday, there was a study they brought down at the Symposium yesterday that from a Wall Street Journal, how I realized AI was making me stupid and what I do now. So basically the article was talking about the fears of AI. So I was thinking about your question in 25 years from now, what's going to look like. So I'm wondering if you could, you're all amazingly educated, but I'm thinking of the 2-year-olds now, in 25 years from now, with AI, how would you suggest being able to live within this, and as it gets even greater and greater, all these systems, how to make that work within the fear of the next 25 years, the generation of the kids actually learning to learn.
It's a great question.
You know what I mean? Thanks.
Yeah. I mean, I'll throw out my own. I mean, I feel like, we all can become overly reliant on technology and never actually understand the fundamentals of what's underneath it. I think, it's a blessing that we have our teachers here who are actually teaching kids at a fundamental level, like what is geography, how does it work? And while AP Human Geography may be more on the kind of social sciencey side of geography, right? We have all these geo-STEM disciplines that are out there that I think it's important for us to teach the kids the fundamentals because we run the risk, right, where they're just running around with the new device, billions of devices that do the work for them, and they don't understand what's at the core. And so how do you actually trust what's coming out of this network of connected systems? It may be better, it may be more accurate, it may be more precise, it may have more global coverage, but if you don't understand what's under the hood, how can you trust it? And I think that's a real challenge. So I do think, our teachers have a real challenge and do a great job with it of helping the kids understand the fundamentals before you unleash them into a world that they're just dominated by all these systems that they either take for granted, potentially misuse, or become over-reliant on. There's always those studies of, you know, the person who used Google Maps, or I don't want to blame Google Maps, but you know, they use one of the routing engines and it, you know, then they like run over a cliff or something. You know, it's like, come on, man. You know, you don't just have to stare at the map. You can actually use common sense, but you also need to understand what's under the hood. I don't know. Do you have any answers?
Yeah, I completely agree with understanding the fundamentals. So in the ocean sphere and the weather sphere, there's a lot of excitement around using AI for weather forecasting and ocean modeling. And I think there is a lot of potential there, but we cannot break the rules of physics. And the thing about AI is unless it's specifically been trained to understand the rules of physics, it's just going off of machine learning, right? It's just going off of the data set, and it can hallucinate. And it might say that something is going to be possible that actually is not possible if you understand the laws of physics. But what I fear is if we have a generation that doesn't understand those fundamentals, they won't catch that mistake. So it is so important to have the fundamentals so that we can work in tandem and in partnership with AI, leverage its benefits, but not be hoodwinked by it.
Pete?
I have a lot of opinions, but I think we're at time, I believe.
All right. Fair enough. Well, hey, thanks for the questions. Thanks for your time. Thanks to our panelists. Let's give them a warm round of applause.